Welcome back. Glad you could join us. Let's talk about physics. Today's video lecture is for Thursday, September 3rd, and it covers the reading in Chapter 4, Section 3. It is about average acceleration and instantaneous acceleration for motion in 2 or 3 dimensions. Again, I will emphasize, just like I did in the previous lecture where we talked about position, displacement, and velocity, both average velocity and instantaneous velocity, that none of the definitions of kinematic quantities that we started with in Chapter 2 are going to change. Same definitions for all these things as we had in Chapter 2. The only thing that's different now in Chapter 4 is that we have 2 or 3-dimensional motion, and so we have to be very careful that all vector quantities are treated by their components. Okay, so starting with definitions, just reminding you, first we'll do average acceleration, its definition, then instantaneous. So average acceleration is defined to be change in velocity divided by time interval, just like in Chapter 2. Here's the notation. A arrow with a subscript AVG, and it's defined to be change in velocity vector, delta V arrow over delta T. And because it's delta V arrow, V vector, everything must be treated separately by X, Y, and even Z components. So what you really have to do to find A average now is look at the expression I have after the equal sign on the right. You have to find the change in the X component of the velocity, delta V sub X, and divide that by delta T and multiply by I hat. Add to that the change in the Y component of the velocity, delta V sub Y, divide that by delta T and multiply by J hat. Add to that the change in the Z component of the velocity, delta V sub Z. Divide that by delta T and multiply by K hat. And you have A average vector. Same definition as Chapter 2, just more terms to keep track of. Then the definition of instantaneous acceleration. And again, same definition as in Chapter 2. Take the average acceleration and expression in the limit as the time interval approaches 0 or becomes infinitesimally small. And what you end up with, just like in Chapter 2, is the derivative of the velocity with respect to time, also called the rate of change of the velocity. So here's the notation. A arrow, instantaneous acceleration, is the limit as delta t goes to 0 of delta v over delta t, but that we just write as the derivative of v arrow with respect to time, dv arrow over dt. But again, what you have to do is work separately with x, y, and z components. So to compute the instantaneous acceleration vector, here's what you do. Take the derivative of the x velocity with respect to time, dvx dt, and multiply that by I hat. Add to that the derivative of the y velocity with respect to time, dvy over dt, and multiply that by j hat. Add to that the derivative of the z velocity with respect to time, dvz dt, and multiply by k hat. And you will have the instantaneous acceleration. Something to note, by definition, the derivative of the x velocity with respect to time, dvx dt, that's the x component of the acceleration, a sub x. And the derivative of the y velocity with respect to time, dvy dt, is the y component of the acceleration. And the derivative of the z velocity with respect to time, dvz dt is the z component of the acceleration. Every vector must be treated separately by its components, x, y, and for full three-dimensional motion, z. So we're just going to be applying these definitions to objects moving around in 2 or 3 dimensions. Here's one special case, again building from chapter 2. How about if the particle is moving around, let's say in 3-dimensional space, and we know that its acceleration vector is constant as it moves. Remember, that's constant acceleration motion. We had special equations in chapter 2 called the constant acceleration equations that we could use to study the motion of a particle if its acceleration is constant. We still do that here. Okay? Let's talk about that for a minute. So I'm looking now at a special case. Constant acceleration motion in 2 or more dimensions. And what I've done is make a table with 3 columns. There's a column for x components, and one for y components, and one for z components, because we have to work separately with components. And all I've done is, for each column, write the corresponding constant acceleration equation. Row number 1 in this table is constant acceleration equation number 1, which in chapter 2, I'll write over here to the side. Here's how we wrote this in chapter 2. V equals V initial plus AT. And that was good enough in chapter 2 because the particle just moved along one dimension, one line, one axis. Okay, writing it like that is no longer good enough, that equation. The whole equation is no longer good enough. What you must do is you must write a separate version of this constant acceleration equation number 1 for each of the 3 components, x, y, and z. And that is what I have done in the first main row of this table. I have taken v equals v initial plus at, and on every v symbol and every a symbol, I've added a subscript, either an x or a y or a z, to denote x component, y component, z component. So look at the first entry here in this row. I just highlighted it. V sub x equals v initial x component plus a sub x times t. So that says you have to work totally with x components only for that equation. The final x velocity equals the initial x velocity plus the constant x acceleration times t. Then, in the next column, there's a y component version of that equation. The final y velocity equals the initial y velocity plus the constant y acceleration times t. And then in the third column, there's a z component version of that equation. The final z velocity equals the initial z velocity plus the constant z acceleration times t. You have to work with the components separately. Now, the next row in this table is based off of what I called constant acceleration equation 2, which I'll remind you by writing over here to the side what it looked like, assuming our particle was moving on an x-axis. X final equals x initial plus v initial t plus 1/2 at squared. That's how we wrote it in chapter 2 when we just had a particle moving on an x-axis. This is no longer sufficient. Instead, you have to write 3 different versions of that expression. One just for x, one just for y, and one just for z. And every v symbol and every a symbol must have a subscript, either an x or a y or a z. Every single v and every single a must have a subscript. Okay? So, for the first column, here's the x version of constant acceleration equation number 2. The change in the x coordinate equals the initial x velocity times t plus 1/2 times the constant x acceleration times t squared. And then you have a version for y. The change in the y-coordinate of the particle equals the initial y velocity times t plus 1/2 times the constant y acceleration times t squared. And then in the third, the change in the z coordinate equals the initial z velocity times t plus 1/2 times the constant z acceleration times time squared. And then the third, or the final row in this table, which I'll label that row with a 3, is what I would have called constant acceleration equation number 3. I'll write it over here on the right the way we did in chapter 2, assuming the particle moved along an x-axis. V final squared equals V initial squared plus 2 times the acceleration times delta x. But that way of writing it is no longer sufficient. We must now write 3 versions of it, one for x, one for y, one for z, where every v and every a must have a subscript. Every v symbol and every a symbol must have a subscript, either an x or a y or a z. So in the first column, Vx final squared equals V initial x squared plus 2 times the constant x acceleration times the change in the x coordinate. And then a similar equation for y components and a similar equation for z. So this table is very handy if we have a particle moving around in 2 or 3 dimensions and we know its acceleration is constant. Let me close this slide by giving you a very important tip. Here it is at the bottom of the screen. Do not mix the columns in this table. The 3 components of all those vectors are independent of each other. In other words, you would never have an equation that would look, for example, like this. I'll write it over here. V final x equals V initial x plus a sub y times t. You can see that. Let me scoot it up just a bit. Whoops. Scoot it up just a bit. There you go. Okay. Notice what I've done there. I've written one of the constant acceleration equations, the first one, but I've mixed subscripts. I've got an x subscript on v final and an x subscript on v initial, but a y subscript on acceleration. Never, never, never can you do that. It's not the way vectors work. It's not vector algebra, correct vector algebra. So those are the main ideas for Chapter 4, Section 3. So now what I want us to do is a little bit of practice. We'll do a 2-dimensional version, okay? Let me bring this up just a little more. A little more. Okay. Let me describe what's going on and show you and explain a little bit what's happening in the picture, because the picture is not terribly easy to read. The scenario goes like this. We have figures A, B, and C here below. Here's A, here's B, here's C. And these represent 3 different situations in which we're plotting x, the x-coordinate, and the y-coordinate as a function of time for a particle that's moving in the xy plane. And again, because it may be difficult to read, I'll label these axes a little bit larger. This first graph under A is x versus t. And then the second graph is y versus t. And it'll be the same kind of thing for B and C. And we have, in each of these 3 situations, shown by graphs A, B, and C, we have a particle that's moving with constant acceleration. And the graphs are all drawn to scale just to help you kind of visualize. And what we are to do for each situation, one at a time, A, B, and C, is to decide which of the pictures shown in part D is down here, which of the vectors shown in part D represents the acceleration vector of the particle. Now, picture D is an xy coordinate system. X and y are the axes. And then there are just 8 numbered arrows, all with their tails at the origin, and the main thing about them is the direction they point in. You can see vector 1, if you look carefully, points in the negative x direction. Vector 2 points up and to the left, i.e. into the second quadrant. Vector 3 points in positive y. Vector 4 points up and to the right, into the first quadrant, and so forth. You've got 8 different directions for the acceleration vector. So we are to take the situations. I'm going to do situation A with you, which is showing me how the x-coordinate of a particle depends on time, and the y-coordinate, that same particle, because it's moving around in 2 dimensions. So you got to know how x depends on t and y depends on t. And these graphs are telling me that. And based on those graphs alone, I can tell you which way, roughly, the acceleration is going to point. How are we going to possibly figure that out? Well, for one thing, I know the particle is moving with constant acceleration. So the constant acceleration equations in that table I just showed you can be used. But I got to apply them separately for x and y. So let's take graph A and let's just look at the x graph. X versus t. Okay? Right up there in the top left graph. The main thing to note about that graph of x versus t, you just look at it. It's linear. Yes? It's linear. And it starts from the origin. So if I want to apply constant acceleration equation for x versus t, it'll be constant acceleration equation 2, because that's x and t. Let me write it over here to the side. X equals x initial plus v initial xt plus 1/2 ax t squared. Every v symbol has an x subscript. Every a symbol has an x subscript. The x initial is 0, right? Because it starts at the origin. I can tell that from the graph. And because that x and t equation is quadratic in t, but the graph is not quadratic, it's linear, I can deduce that it must be the case that for this particle, a sub x equals 0. Let me make that 0 better. Yes? So that the underlying equation for this particle is x equals v initial xt. It's that simple for part A here. And x versus t is linear, just like I see. Well, if a sub x is 0, let's mark that down, because now I know what the x acceleration of particle A is. It's 0. Okay? I can deduce that from the fact that x versus t is linear. All right? So I figured out what a sub x is in situation A. It's 0. Now let's look at the yt graph in situation A. Let me write over here on the right side constant acceleration equation number 2 for y coordinates. Y equals y initial plus v initial yt plus 1/2 ay t squared. Every v symbol has a subscript y, and the a symbol has a subscript y. We're working with y coordinates now. I know, again, from the graph of y versus t, that it starts at the origin. So y initial is 0. Sure, it looks like it starts flat at the origin. And remember, the slope of the tangent line would be velocity. But this is y versus t, so the slope of the tangent would be y velocity. So it looks to me like the y initial velocity is 0. And then it curves upward. In fact, what it is a parabola opening upward. So the coefficient of the quadratic term must be positive. Well, the coefficient of the quadratic term, because here's all that's left in my formula, is y equals 1/2 a sub y t squared. But that parabola for y versus t opens up, so a sub y must be positive. I can't give you an actual number, but I can tell you it's positive. Just based on that graph of y versus t. So here I am in situation A. I've deduced that this particle is moving such that its x acceleration is 0 and its y acceleration is greater than 0. what must the vector A look like if we were to sketch it in the xy plane? So now the axes are x and y. So I'm going to draw an arrow, tail at the origin just for convenience, but it's got to be a vector, an arrow with 0x component and a positive y component. The only thing that is possible then is a vector that points straight up along the plus y direction. Yes? Then a sub y is greater than 0 and a sub x is equal to 0. That's got to be what the acceleration vector looks like in terms of the direction it points. Therefore, I know in that picture D down at the bottom which of the numbered arrows is the correct one for the acceleration. Arrow 3. So the answer for part A, based on those graphs of x versus t and y versus t, is that the acceleration vector must be represented by the arrow labeled number 3. Okay, so here's what I want you to do. This is going to be one of our class engagement exercises. So you'll go to Blackboard where you'll see that I've created an assignment for it, class engagement exercise for this class. And I want you to go through the same kind of analysis that I just did for case A, but I want you to do it for case B and case C. And all you have to do is tell me for case B which of the numbered arrows in the figure down here, 1 through 8, represents the acceleration vector for case B, and then for case C, which of the numbered arrows, 1 through 8, represents the acceleration vector. Okay? You don't even have to give me any discussion. Just tell me the answer for B and then for C. And that will be our class engagement exercise. And that's all I have for this video.